So in this example problem, we're going to use the 2D equilibrium equations to solve for the unknown forces at our supports. So in this example, we have a bar AB that has a pin at point A, and it has a smooth contact at point B. All right. So using this information, we're asked to determine the horizontal and vertical components of the reaction at pin A. So the first thing we're going to do is we're going to draw our free body diagram. So in this case, we're going to draw the outline shape of our of the rigid body. So in this case, it looks something like this. All right. The next step we're going to do is, but when we draw our outline shape, we can label the points on the body. All right, and we can label any critical dimensions that we need. So we know that between point A and point B, it's 0.75 meters. We know that it's at a 30-degree angle with the negative x-axis. We know that between point A and 1 meter, we'll have an applied load, and an extra half meter away, we will have a couple moment. Okay, so once we have all of our dimensions written, we can apply all of our reaction forces. So we know that at point B, we'll have a reaction force, NB. All right, and at point A, we'll have a reaction force, A of x, and A of y due to the pin there. So a pin allows for rotation and a smooth but no translation, while a rocker joint allows for rotation and translation along every direction except normal to the point of contact. All right. So once we have those unknown forces drawn, we have to draw any applied forces that are part of the system. So we have a 60 Newton force that's applied 1 meter away from point A, and we have a negative a clockwise couple moment of 90 Newton meters acting 1 meter away as well. All right. So these are our. So once we have a free body diagram drawn, we can now look at applying our equilibrium equations. So that's our second step. Okay. So when you're applying the equilibrium equations, you want to try to minimize the amount of unknowns that would be in any equilibrium equation. This will make solving the problems a lot simpler. So the one thing we know, we have three equilibrium equations that we can use. Alright, so in this case, where you can use sum of the forces in the x direction is equal to 0, the sum of the forces in the y direction is equal to 0, and the sum of the moments about a point will be equal to 0. So we know that, so we're going to use the sum of the moments about a point first. And the reason we're going to do that is we can simplify we can make our calculations a lot simpler. So if we sum the moments about point A, and we set that equal to 0, the big benefit of doing this is that A of x and A of y will not produce any moment about point A because they have no moment arm. They're applied at the point. If you apply a force at a point, it can't generate a moment about that point. So if we do that, we'll end up with the moment caused by the normal force at point B times the moment arm there. So the moment arm in this case is 0.75 meters. All right, that's nice because we know that that NB is going to be normal to the length from point A to point B, so we don't have to modify the moment arm at all. And then we're going to have the 60 Newton force times 1 meter will create a moment. And if we use the right hand rule, it will create a clockwise moment about point A, so it should be equal to, it could be a negative moment. All right, and then we have to include the 90 Newton meter moment that's applied at the end of the bar, so that's going to be equal to minus 90 Newton meters because it's clockwise. Okay, so if we rearrange all of these, what we end up getting is we get NB times 75, 0.75 meters is equal to 150 Newton meters. All right, so N of B is going to be equal to 200 newtons. All right, so once we have N of B, we can now use our other two equilibrium equations. So we'll start with the sum of the forces in the x first. So if we sum all of our forces along the x direction and set them equal to 0, what we'll end up getting is we'll get N of B times the cosine of 60 degrees. So we know that this triangle here to be 60 degrees. So so how do we know this? Okay. Yeah, so if this is 60 degrees, this would be yeah. So it's a 60-degree angle, and so we would be going along the negative x-axis, and then we have to add in a of x. So we get a of x would be equal to uh, NB, which is 200 newtons, times the cosine of 60 degrees, which is 1/2. So it's going to be equal to 100 newtons. And then we can sum the forces in the y direction last. All right, and then if we do that, we'll end up getting a of y minus NB sine of 60 degrees minus 60 newtons, which was the applied force. So we would get a of y would be equal to NB, which is equal to 200 newtons, times sine of 60 degrees, which is equal to radical 3 over 2, plus 60 newtons. All right, if we add this all up together, they'll be equal to 233.21 newtons, and then we round to three significant figures. We would get a of y is equal to 200, approximately equal to 233 newtons. All right, so in these types of problems, the two critical steps are you're going to draw your free body diagram. It's very important that you get the supporting reaction forces correct. All right, you must. If you don't correctly identify the reaction forces, the rest of your calculations will be incorrect because you won't properly be able to apply your unknown forces and won't be able to apply the equilibrium equations correctly. So once you have your free body diagram, you'll use the free body diagram and the equilibrium equations to solve for any of the unknown forces in your system. Okay, and that is it for these types of problems.